In this tutorial, I will cover the basics of digital number systems, including decimal, binary, and hexadecimal. All number systems work using digits. Each digit increments to a certain number and then recycles to 0, and the digit to the left then increments by 1, and the cycle repeats. Decimal is base 10, as indicated by the name dec, and is a number system we're very familiar with as we use it in everyday life. Base 10 means the digits in each column can have 10 states. The first digit in a base 10 system represents the unit, and the second digit represents the 10. The unit digit counts from 0 to 9, and then it returns to 0. As this recycles, the 10 digit increments. When the unit digit reaches 9 again, it recycles, and the 10 digit increments again. When the 10 and the unit digit reach 9, they both recycle, and the third digit, which is the 100 digit, is incremented. Binary is base 2, as indicated by the name bin, meaning each digit only has 2 states. Digit 0 counts from 0 to 1 and then recycles back to 0, and digit 1 increments from 0 to 1. When digit 0 and digit 1 both become 1, they recycle to 0 and then digit 2 becomes 1. You can see a parallel with the base 10 system. The only difference is the digits recycle after 2 states instead of 10. Hexadecimal is base 16, meaning the digits have 16 states. There are not 16 numerical characters, and so letters A to F are used to fill in. Digit 0 increments to 16, which is represented by the letter F, and then recycles back to 0, and digit 1 increments. When digit 0 and digit 1 both become F, they both recycle, and then digit 2 increments, and so on. Digital systems store and interpret all numbers as binary bits. A single bit has 2 possible states, 0 and 1. This can also be referred to as high or low, or set and clear. Bits can be represented, transmitted, or stored by anything that can have 2 distinct states, such as a switch being open or closed, a button being pressed or released, a light being on or off, and so on. When bits are grouped together, they create digital words. 2 bits grouped together, shown here as digits D0 and D1, have 4 possible states, 00, 01, 10, and 11, which represent the decimal values of 0, 1, 2, and 3 respectively. This is the truth table for a 2-bit word. Note that there are 4 states depicted by each line. If I add a third bit to make a 3-bit word, there are now 8 possible states, as I can have the existing 4 states with the third bit clear, and then repeat them with the third bit set. Notice also that for each bit column, the bit becomes 1 for the first time with rising powers of 2. This means that each additional bit adds a power of 2 to the decimal value which the word represents. A binary word with only the first bit set has a value of 1. If I move that bit 1 place to the left, the value doubles to 2, and then 4, and then 8, and so on. Each of these numbers is an increasing power of 2, and so can be written as 2 to the power 0, which equals 1, 2 to the power 1, which equals 2, 2 to the power 2, which equals 4, 2 to the power 3, which equals 8, and so on. This means that each column is a rising power of 2, which has parallels with the decimal and hexadecimal systems. In decimal, each column is a rising power of 10. And in hexadecimal, each column is a rising power of 16. When programmers refer to binary words, they call the bit on the far right the least significant bit, and the bit on the far left the most significant bit. I have a 16-bit binary word with a random value. The decimal value of this bit combination is 19,164. The most significant bit and least significant bit are both clear. If I set the least significant bit, the value increases by 1 to 19,165, not a very significant change compared to the overall value of the number. If I now set the most significant bit, the value increases by 2 to the power 15, to 51,933, which is a much larger or more significant amount. Each bit is numbered, starting with the least significant bit as bit 0, and the most significant bit is set by the length of the word. For an 8-bit word, the most significant bit is 7. For a 16-bit word, the most significant bit is 15. For a 32-bit word, the most significant bit is 31. In embedded software, a 4-bit word is called a nibble, an 8-bit word is called a byte, a 16-bit word is called a short, a 32-bit word is called a long, and a 64-bit word is called a long. Typically, programmers will refer to these numbers as integers because they can only store integer values, or whole numbers. Integers can also be signed or unsigned. An unsigned number will only hold positive values, while a signed integer can hold positive and negative values. There's no physical difference, it's just the way the bits are interpreted. A 16-bit unsigned integer will hold 65,536 states. If all bits are 0, this gives a value of 0. If I increment this by 1, I get the value of 1. All bits set give a value of 65,535, which is 2 to the power 16 minus 1. If I increment this by 1, all the digits roll over back to 0 and the value returns to 0. If I set all bits except for the most significant bit, like so, this gives a decimal value of 32,767. If I then increment, the bits all roll over and the most significant bit becomes set, the same behaviour which we saw earlier. The decimal value is now 32,768. However, if that same 16-bit integer is made signed, the most significant bit becomes the sign bit, and the integer can only hold half that value, as now only 15 bits are available to hold the value. Again, all bits 0 give a value of 0. 15 of the 16 bits being set will give a value of 32,767 as before. But if I then add 1, which will now set the sign bit, the value does not become 32,768, but instead becomes minus 32,768. There is no difference to the bit behaviour. As shown earlier, all the bits in the columns were set, so incrementing the value by 1 caused all the columns to roll over back to 0, and the digit in the next column along became set. But because this word is now being considered signed, the decimal value it represents is now minus 32,768. If I continue to add 1, the bit sequence will continue to increment as before, but the decimal value they represent will count upward from minus 32,768 until eventually, when all 16 bits are now set, the decimal value will be minus 1. And then with the final increment, they all roll over back to 0 and the decimal value becomes 0 once again. When using signed integers, the most significant bit can be thought of as the minus sign. If it is set, then the number is negative. The value is then held by the remaining bits. I have a combination of bits with the most significant bit clear. The value it represents is 23,139. If I treat this number as an unsigned integer and set the most significant bit, the number becomes decimal 55,907. If I treat it as a signed integer, then the new number will be negative 9,629. Hexadecimal is base 16. The truth table shows 16 binary states from 0000 to 1111 and displays their equivalent decimal and hexadecimal values. See how the decimal values recycle after 10 states, but the hexadecimal values continue until the 16th state, and the letters A to F are used to represent the states once the numerical characters have run out. If 4 binary bits hold 16 states, then a single hexadecimal digit simply represents a block of 4 binary digits, or a nibble, which is very useful in embedded programming. In the next tutorial, I will demonstrate how to perform basic numerical conversions between binary, decimal, and hexadecimal.